So I wanted to take a minute. I've been talking about differentiability with a lot of going straight to the definition of a derivative being a two-sided limit, where we're finding the slope between 2 points and moving them infinitely close together. But there is an alternative way of thinking about what does differentiable mean, and that's graphically. So we can think that a function is differentiable at a point. So notice I'm talking about at a point, not over the whole domain, but at a point, if it's what we call locally linear. This means that if you zoom in close enough to that point, the function starts to look linear. In other words, the function begins to look like its tangent line. This is a nice graphical way to think about differentiability because it allows us to then say, well, if I'm close to a point of tangency, my tangent line looking like my function means, well, I can use the tangent line to estimate function values close to the point of tangency. Right now, that's not going to seem super helpful because of how much work it is to find the slope of the tangent and write the equation of the tangent. But we'll be learning some shortcuts for calculating derivatives. And when you know those shortcuts, finding a derivative is not super hard. And it's a lot easier to plug x's like 3.0278 into a linear function than it is to plug into, say, a quartic polynomial or a fifth degree polynomial. So the math is easier if we can use a tangent line to estimate, because there are a lot of times in life where we don't actually need the exact value, we just need something close. And if we can use a tangent line to get that close enough, well, that's a lot easier. So an example of this would be, let's say I'm asked to write the equation of the tangent line for the function x squared when x is 3, and then use this tangent line to estimate f of 3.1. I know this is an example where you're like, well, it's not that hard for me to square 3.1 even without a calculator, but I just want to go through the work here. Once we start getting our shortcuts for derivatives, these will get more complex, and you'll start to see why this is helpful for us. So to find the equation of a tangent line, I need a point and a slope. I'm going to find the point first. So the point, the x is 3, because they tell me that. I plug 3 into my function. I get the y coordinate of 9. For the slope, well, I need to find the slope between the point that I have and a point that's h to the right of it. So I'm going to be using the other point, 3 plus h, and 3 plus h squared for the coordinates. So I'll be doing the limit as h approaches 0 of 3 plus h squared minus 9, the change in y's, over 3 plus h minus h, the change in x's. Multiplying out my 3 plus h squared gives me 9 plus 6h plus h squared minus 9. Combining like terms on the bottom, that shouldn't be an h here, that should be a 3. Gives me just h. The 9's cancel. I can divide what's left on top by h. So I have the limit as h approaches 0 of 6 plus h, which is 6. So now that I have my point and the slope, the equation of my tangent is y minus 9 equals 6 times the quantity x minus 3. Or if you prefer to have the y isolated, I'd have 6 times the quantity x minus 3 plus 9. So then to estimate f of 3.1, I just plug 3.1 in for x in my tangent line. So I'm going to have 6 times 3.1 minus 3 plus 9. Well, 3.1 minus 3 is 0.1 times 6 is 0.6. So this is 9.6. If I actually wanted to find f of 3.1 exactly, well, that's 3.1 squared. So 3.1 times 3.1, which is 9.61. So my estimate is actually pretty good using the tangent line.